Very good. So let's reconvene. So we continue, and can you share the screen again? And unmute yourself, Cornelia and Anton.
Anton will continue, but he has still some small problems.
Ja, es funktioniert nicht. Versuchen Sie es bitte später erneut.
A few more minutes. Scheinen kann der Anton nicht mehr seinen Bildschirm teilen. Anton,
Ja, ist schon klein. Ja. Hast du das dann wieder gesagt, dass sie mir das erlauben kann?
Ja, aber du hast es wahrscheinlich schon.
Ja, ich versuche.
Ja, du bist schon Co-Host.
Co-Host, deswegen,
Ja.
ich mache es aber nochmals gleich.
Du kannst es bei mir machen.
Okay, dann gehe ich rüber, dann mache ich das.
Ja.
Aber jetzt geht es natürlich so Teil 3.
Ja. Hier.
Teil 3.
Wo ist denn das? Wo fängt das denn an? Ah, hier. Hier.
Muss ich dann mit deinem Kopfhörer arbeiten?
Nee, musst du nicht.
Und wie ist das, die Folie runter? Das geht dann.
Genau, das mache ich mit dem hier einfach.
Ja.
Oder?
Okay.
Probier mal aus. Nehmen wir dann noch mit Bild.
Passt schon.
Nee, mit Bild. Und hier mal.
Kann man doch mal.
Ja.
So, can you hear me?
Nee, doch.
Yeah. So I'm sorry for this. Sorry for this delay. Now we are back to Canning's models, and in a somewhat again more general setting than what Cornelia presented just before. Remember, Cornelia restricted to Canning's models with Dirichlet type weights, right? So where these weights, the so to speak reproductive weights of these individuals that are assigned them in an exchangeable way by chance are ratios of yi divided through the sum of all those y's. And here we are again back to Canning's models with a general paint box, not necessarily of Dirichlet type. And those paint boxes can also vary in a non-homogeneous manner as the capital N increases, right? And let me recall quite briefly, these are the situations. In every generation, we have those paint boxes IID. and they are mass partitions. They sum to 1, and this is the magic square, where we have in the vertical direction, so to speak, the individuals, and in the horizontal direction, length 1. And we will decrease the length of those stripes for the wild type individuals by this factor 1 minus Sn. I already announced an hour ago that the forward step is in that manner when we know that in generation G minus 1 we have K wild type individuals, their weights are reduced. Then we have a picture like this, and we now assign the mothers to the daughters in the very same way as in the Wright-Fisher situation, by throwing uniforms, but we throw them into the colored, into this blue or red colored region, and look into which stripe the RJ, R for real mother, right? When the R1, as it is here, when the R1 goes into like J, into this stripe JN, then N is the mother of the R1, of the individual one, and so on. And the number of daughters is this Canning's offspring number nu I. That's the number of J's for which the RJ falls into this colored part of the stripe, right? And now the backward perspective, going back and looking at the potential ancestral lineages. Well, you see, this is a new thing. And a few years ago, this was an idea of Dario Spano and Adrian, who is in the audience, as I saw. And they came up with what they call the Wright-Fisher ancestral selection graph. And at one time I heard a talk by Adrian, and I thought, well, this must there are these geometrics coming up in a magic way in their calculations. Where are they sitting in and then of course in such a nice opportunity as we have now in the one world situation, we merged, right? And now he's now part of this team of authors, one of the 4 that that wrote this work we are now telling about. And this is now one step of this backward perspective, the one step of the ancestral selection graph. Without knowing a priori the number of wild type individuals in generation G-1, right? That's the idea of the ancestral selection graph. Construct potential ancestral lineages and do the coloring a posteriori, right? And we saw already in the very first part in the introduction that when we will have an equilibrium situation of this ancestral selection graph, we can run it for a long time back. Then we are close to or in the equilibrium situation then, and then we can ask, does the number of ancestral lineages, potential ancestral lineages in equilibrium, does it capture this one red guy which was initially present and which, I mean, I could now switch to epidemiology and say, well, there was this one bad guy at the beginning that infected everything in the end, right? But here it's much nicer. So we have a beneficial type, beneficial mutant that fixates in the population. It's so much nicer to speak about this. But actually, there are these obvious parallels, right? Okay, but what is here this one step back? That's the Canning's ancestral selection graph. And you see, it's just as before, but this blue and red thing of this gamma-shaped curve, which we had before, it's now hidden, right? We don't know how many we don't care actually at this step how many individuals had which color. And now what we do is we throw potential choices, right? Let for the daughter individual number J, let UJ1, UJ2, and so on be a sequence of IID uniforms on the entire square. So this is the UJ1, which you see here. Now, this is the UJ2. And this is a good, this is to stop when some of those U's falls into what is here the purple region, right? I mean, we have here this thing which has a width 1 minus Sn, the purple thing, and then we have the pink thing which has a width Sn, right? And we throw these U's as long as we hit the purple thing for the first time. And that's a geometric number of trials. Here are the geometrics, right? That's the GJ, that's the trials up to the first success when we hit this core area, the purple area. That's geometric with parameter 1 minus Sn. Now say that an individual I is a potential parent of individual J if on the way to the first success hitting the purple area, right? If on that way the stripe of the stripe of this interval, the Ji, is hit by at least one of those, right? So here in this situation where we needed 2 trials to hit the purple area, we have 2 potential parents. It's the UJ1, which falls wherever it falls, right? And it's the UJ2, and the 2 is already the number we need. Now, given the number k of wild-type individuals in generation G-1, the individuals J's type can now be determined in a 2-step manner, right? So we do the coloring afterwards. First, we construct all the potential parents, then choose out of n randomly those that are of wild type. I mean, that's an exchangeable situation. And namely, say now which stripes are colored blue. And now comes the punchline. J is of wild type if and only if all the potential parents of J avoid the red region, right? If and only if all the potential parents fall into blue stripes. This is because after assigning types to generations, we can recover the real parents. We can embed this first thing, which I told you already at the beginning, into this more complicated situation by saying that RJ is the first one of those UJs that falls into the either red or blue colored region, right? These are then the real parents. And the fact is that the individual J is of wild type if and only if, after the coloring of the generation G-1, all its potential parents are of wild type. And as a consequence, what we can do with one daughter individual, we can do with a sample taken from generation G. A sample of individuals are all of wild type if and only if, after the coloring of generation, here I should say G-1, generation G-1, all their potential parents are of wild type. And then we can say this can be iterated back over the generations, and it leads to a sampling duality. A sample of individuals in generation G are all of wild type if and only if all their potential ancestors in generation 0 are of wild type, right? It must not touch any beneficial individual. If it's just one at this early generation, then it must avoid this one thing, and then and only then are all the late comers of wild type. Now it's all a question of counting, right? We need to count the number of potential ancestors. And this is a branching, coalescing process as far as the lines are concerned. And it's a Markov process on the positive integers, excluding 0, as far as the number is concerned, right? And we see already the branching step. This was easy. It had an offspring distribution, which was geometric. This was this geometric, which I mentioned earlier. And the coalescence step is a sorting balls into boxes story, right? Because we have our sum of geometrics, and these guys are then uniform in the vertical axis, right? So they fall into their intervals. And it's just like balls into boxes, and the boxes have their sizes Wi, right? And so this makes the thing a little bit delicate for the analysis of this number of lines. I will come to that in a minute. But the crucial nice theorem is that the fixation probability for a single mutant equals, just as in the Neuhauser-Krohn situation, right? It's the same conceptual business as I explained before. It's the expectation of the ratio of potential ancestral lineages to n, right? The fraction of boxes that are occupied in this equilibrium. That's the fixation probability, right? And now we are faced with a, can one say, classical problem, that we have a process where we have a branching and a coalescence step, right? So these negative binomials, the sum of the geometrics, it's the upward step, and the sorting of that so many into the random boxes is the downward step. And the question is how to characterize, how to analyze the equilibrium, and actually only the expectation in equilibrium. So it's a fairly classically looking thing, but it took us quite some effort and quite a while to push through. And some of you may even have heard a talk in Warwick at one time, where we didn't have the whole story. We have it now since last January, where that paper appeared in EJP, and in the months before, we completed this situation. Now, before I tell you the result, just a little feeling, the larger Sn, the larger is this, the more we have an upward tendency of this branching, right? And the larger the V, the offspring variance is, the more we have a coalescence business, because the offspring variance and the coalescence is in duality. And so the hope would be that this thing is where those two drifts cancel each other, and doing a small calculation shows that this would be compatible with the Holden formula, right? But now, what about the hard result? Assume, or the hard message, not just soft explanations. Assume paint boxes with an asymptotic offspring variance V. Then this is, as Cornelia explained it before, right? It's the asymptotics of this n squared times the expectation of the second moment of the weights. Assume that this converges as n tends to infinity to some v. We have to require this, because otherwise the weights can differ from n to n dash as n increases. These weights can differ. Other than in the Dirichlet type case, where they are all governed by the same yi's. This was the second part before. Well, and another third moment condition. And by the way, this implies Mölle's criterion for the Kingman attraction, right? And with these assumptions, which are also fulfilled in a Dirichlet paint box, and also in a situation which Cornelia described in the second part, Dirichlet type weights, provided that the fourth moment of y1 is finite, then we have the following theorem. Under these conditions, and for a moderately weak selection, where the Sn is of the asymptotics n to the minus b, where the b is between 2/3 and 1, right? So it's quite weak here, the selection. It's more towards the n to the minus 1 thing. Then the Holden asymptotics for the fixation probability holds. This was already the state of the knowledge when I gave quite some time ago this talk in Warwick. And this was, the proof works by a coupling of the counting process of potential ancestors. On one hand, in the Canning's ASG, and the counting process of potential ancestors in the Moran ASG, which I explained in the first part of the talk, right? So this classical Moran ASG and this animal, which I explained you just a few minutes ago, they can be coupled in this regime of rather weak selection. And this is because the selection does not drive the thing too much up, the number of these potential lineages, and the fluctuations of this number of potential ancestral lineages is not too big, right? So we can control these things, and the station, and we can control the multiple mergers that go beyond 2, right? We can control them for quite a long while in that regime due to the conditions, the moment conditions. And so we can just have a look on the Moran ASG, and there we know already from part 1 that the expectation of the numbers of potential ancestral lineages is perfect for Holden's formula. And so this is the rough sketch of the proof in this first regime. And I will skip this. This is just, we can maybe come back to this. Why do we need just this bound? This is because of the coupling with the Moran Neuhauser-Krohn ancestral selection graph. But now let me turn to what is more recent, namely how to fill this gap from 1/2 to 2/3 and to cover the entire regime of moderately weak selection, right? And this is a little bit more daunting. I mean, this these things here, they say that we need a quite high concentration of these weights, right? I mean, it's more or less, I mean, in the Wright-Fisher case, those powers of the weights, they are deterministic. They would just be 1 over capital N to the power, right? Now here, they may fluctuate, those guys, and we require this growth of moments, right? So under this condition C, together with what I call the asymptotics of variance, right? Which the formula, which I don't want to repeat here, I can just go back and show it to you, the asymptotics of variance here, right? Which gives us the V, the candidate.
So sorry, is it variance or is it second moment of W?
It's asymptotically equal, right? Because this is the other thing is negligible, right? The difference. I mean, here we saw it's the factorial second factorial moment, right? In this AOV, but up to this correction, which is of order 1 over n, we have the same, right? But you are right. I mean, also in the Kolmogorov formula, which I showed in part 1, it's not the variance, but the second factorial moment which shows up, right? But in the slightly supercritical case, this becomes asymptotically equal. But thanks for the question.
Okay, thank you.
Now we go back to this main theorem, which says that under these conditions, the Holden asymptotics again is valid. And maybe before I go to the sketch of this proof, which will then be taken up by Cornelia in the 4th part again, let me mention something which is a nice situation, because you see this paper, the other paper on the strongly moderately strong regime, which Cornelia presented in the part 2, is in a revised form in the arXiv since I think today. We worked hard to arXiv a nice revised version. There were 2 excellent referees of this paper, which hopefully will appear in the Journal of Mathematical Biology, and has a nice tradition there, because a series of very nice papers on Holden's asymptotics have appeared in the JOMB over the decades, right? There was a nice paper by Fred Hoppe in the 90s. There was Atreya's nice contribution, which built on the Kolmogorov result. There was before a paper by Eschel and so on. And one of those referees asked, is it true that in the domain of attraction of the Kingman regime, the Holden asymptotics is automatic, right? Because here we have conditions where we say, if they are true, then we are in the domain of attraction of Kingman, right? We have Möhle's conditions. And this referee asked, can one have a situation where we have a sequence of Canning's models with a paint box that are in the domain of attraction of the Kingman, but violate the Holden asymptotics? And in the arXiv version, we didn't touch this point, but yesterday preparing for this talk, we found an example, and I promise you in the V3 of the archive, which will be, I think, this weekend or whatever, because we will now also resubmit we haven't submitted yet, then you will find this example. This is just an aside. But now let me just comment very briefly and then hand over to Cornelia again on the idea of proof of this main theorem. This is very, very sketchy. Okay, the proof uses again directly this, but not really. Now it uses directly this formula, right? It does not couple with the Moran ancestral selection graph because the assumptions are too weak for this coupling, right? We have such a actually strong selection already. It's still above n to the -1/2, so it's still moderately weak, but it's on the strong side of the moderately weak thing, right? And therefore, we have a high upward tendency and quite a lot of fluctuations. And now we need to control, we need to control this integer valued Markov chain, right? And we want to know what does it do in equilibrium. And this assumption C, this growth of moments, right, is instrumental for controlling the larger downward jump. There are nice results in the literature on the birthday, refined versions of the birthday problem analysis. And we could make use of such things to control the downward jumps of this line counting process. So to control that not too many multiple balls land in the same box, although the boxes are random and so on. We, of course, then had comparisons with other processes that were easier to handle, random walks. In certain regions, we had a central region around the center of attraction, and this was not left for a long time, right? Larger than polynomial time. And when we were outside of this central region, then we came back quickly. So all these things had to be controlled, and we were able to do this. This is a new chapter in the revision which appeared in EJP in this January. Okay, now I hand over to Cornelia again. We change seats.
Okay. Okay. So, okay, now you hear me? Yeah? Yeah, okay. So this is now the last part of our tandem talk, and it's an outlook on the fixation probabilities in non-Kingman regimes. And this is joint work in progress with Matthias Böckner, again with Florin and Julia Dahmer. And here we consider Canning's models in the domain of attraction of the beta coalescent. And this means, so we again consider Canning's models with selection as before, and we assume again that we have these Dirichlet type paint boxes. So they are constructed with these random variables y, which are all identically distributed, and the weight of the i's parents is given by this yi divided by the sum of the y's. But now we assume that the random variables y, they don't have exponential moments, but they have heavy tails. And we assume that the tails fall as y to the power of minus alpha, where alpha is some number between 1 and 2, and L alpha is just some constant. And again, we assume that without loss of generality, the expectation of these random variables y are 1. Okay. And again, we are interested now. We have the Kennings model with selection with these kind of Dirichlet typed weights. And we are interested in the asymptotic probability of fixation. And the strategy is to use the backward process to calculate this asymptotic probability of fixation. And we can use this because the definition of this backward antithesis selection process was independent of the assumptions on the weights. And also the sampling duality did not use any assumption on the weights. This only came in when we wanted to show the Haldane asymptotics. So the sampling duality holds, and the sampling duality tells us that the probability of fixation is given by of a thing when the beneficial individual is initially present only in a single individual. When the beneficial allele is initially present only in a single individual, then this probability of fixation is equal to the expectation of the equilibrium ancestor selection graph divided by n. So it again remains to find the asymptotic of this expectation of the equilibrium ancestor selection graph. And yeah, now you remember Anton told you that we have at least for the case already in the case when the B is larger than 1.5, we got these problems with the moment conditions. We need these quite hard moment conditions to really control this expectation. But now let us calculate what moments we have now. So we can show that, so of course the first moment is again 1 over n, and the case moment, but now is of this order. And now n to the power, we have for all moments, k larger or equal than 2, the order is not decreasing. It's of the same order. So in fact, this proof, what we used before, that really relies on this the assumption that the moments are decreasing fast enough cannot be used. So we cannot use this coupling with random walks. And the reason is that in fact these moments, they give the probability that if I have k individuals, that they all choose the same parent. Yeah, if we multiply this by n, and these probabilities, they do not decrease with n, but they stay the same. So all these coalescence events are important. We cannot say so again. Okay, that I didn't tell you in detail. So what we did in this center of attraction is that we coupled with a random walk, and this random walk most of the time does only jumps of size 1, and only sometimes it does a bit larger jumps. But due to this moment conditions, we can control the size of these jumps, and we cannot do it in this case. Yeah, but what we can also do here is that we can calculate the pair coalescent probability, and this is of this order. Okay, now we can use again a theorem by Huillet and Möller, and this theorem says us that at least the neutral genealogy of this kind of Dirichlet type Kennings models, they lie in the domain of attraction of a beta coalescent if we rescale time also. So the genealogies rescaled by the factor 1 over Cn, they converge to a continuous beta coalescent. So this means that when we consider our neutral Kennings ancestor selection process, this process should be, in fact, if we rescale time, very close to this beta coalescent. So the following model with selection should be close to our Canning's ancestor selection process with selection. So we consider the following process. So if we have n lines, then we assume that lines merge, so that k lines merge. So we have a jump from n to n minus k plus 1 according to this rate of the beta coalescent. That was the approximating process in the neutral case, but now we have to slow down time by this rate by the factor Cn. And then, in addition, we assume that each line branches at rate Sn. That is, we have a rate to jump from state n to state n plus 1 at rate n times Sn. And so the theorem from Müller suggests that, in fact, this process should be very close to our Canning's ancestor selection process. And for this process, it's easier to guess the equilibrium of this backward process, because we just have the rates, and we can calculate when the upwards and the downwards drift cancel. And we have here the upwards drift, and we have here the downwards drift. And so if one calculates with these rates, it turns out that this is a sum of gamma functions, and one can understand the asymptotics of these gamma functions. So it's asymptotically equal to this this expression here, and then we can solve this, and for the number of lines which we have when this upwards and downwards drift cancel, and one obtains this expression here. So one would guess that the expectation of the equilibrium backward process will have this many lines if this number here is large, because then we can use this asymptotic formula here. And this is the case if alpha minus 1 minus b is larger than 0, or alpha minus 1 is larger than b. And in fact, one also can prove this. And yeah, now the proof is different than we have shown it before in this Kingman attraction regime. What we use is in fact, quite simple trick. So let Q be the generator matrix of this backward process, this coalescing branching process, and P the stationary distribution of this process. Then P times Q is equal to 0. And now, because the state space of this process is finite, we have here only a finite matrix. So when we choose any column vector in R, Rn minus 1, and multiply it to this matrix, then it's again 0. Does not change anything. So now assume that we find a vector h, which is a kind of Lyapunov function, because in fact this vector h is a function, yeah. So here is my so for each I or x in 1 to n, I have here the value h1, which is h of x, which h of x, yeah. And assume now we can find a vector such that this relationship holds. That is, I start in some x, and then I move with qh of x, and when I have moved, I'm still smaller than this value k. Then I can multiply now the p from the left. Then this cancels by this condition here. And here, this is in fact the expectation, because I have here just the sum x px. And here I have the sum kpx, and the sum of px is 1. So I have just an upper bound for my expectation. So the goal is now to find these functions h. And yeah, in fact, this approach where we found this has been developed for also for infinite state spaces in Klin and Sebi. Okay, now we have to find this function hn, and the case we want to choose are for the upper bound. This is the equilibrium, because we want to bound our expectation by the equilibrium, plus some function. Sorry, this is again an h. This should be another letter. So some g, yeah, gn. But what we give from above should be only of smaller order. And for the lower, we also want that we have here this equilibrium, our guess expectation, plus some a little bit smaller term with minus some term which is of smaller order. And to do this, in fact, it works for the upper bound with linear functions. I think I don't have time to explain this. Yeah, it's a bit late. Yeah, and for the this is because this generator here has this very particular form why this works. And for the lower bound, we need quadratic functions to show this. Yeah, and in fact, this technique can also be applied to show the result for the lambda Kanning's ancestor selection process. So it works for this continuous time process, but also for this discrete time process. It's a bit more involved, but it also works if b is smaller than alpha minus 1. And then, as a corollary, we obtain that the probability of fixation is asymptotically equal to this divided by n. And this can be written like this here. And now we have a short look at this formula. So alpha is between 0 and 1. This means alpha alpha is between 1 and 2. So alpha minus 1 is between 0 and 1. So this expression here is larger than 1. So we have a power of Sn, which is, so we have Sn to a power of a number which is larger than 1. So this number here is much, much smaller than Sn. So, and this is in fact what also tells us our intuition, because if we are in this lambda world, we have much more coalescence, and this brings much more variation inside, and so the probability to die out is higher than in this Kingman regime. And we see the same behavior here. We can play here with this parameter L alpha, and the parameter L alpha, this was here in this tail of the distribution of y, and the larger L alpha, the heavier the tail, and therefore we have again the larger are the variations, and therefore the probability of fixation should be again smaller. And this is again the case because this L alpha comes here in a negative exponent. Yeah. Okay, now for the n, I have an overview what we have shown today. So the red part is a backwards approach that we used. So for alpha between 4 and infinity, so this is for the fixation probabilities of Dirichlet type Kanning's ancestor selection processes with this Pareto-like tail, so where we have just this constant L alpha. So if alpha is between 4 and infinity, then for these Dirichlet type weights, or as Anton said, the stronger moment conditions are always fulfilled if alpha is larger or equal than 4. So we can use a backward approach with the coupling with the Moran model to show the formula. So for alpha equal to infinity, we can also, with these Dirichlet type weights, we can also show these stronger moment conditions. So we can also use a backward approach to show the formula for B larger than a half. Then we have a little small gap for the case beta equal to 1.5. And then I just, in the first part of our tandem talk, so where I was talking, I explained you the situation where alpha is between 4 and infinity. We are here in the domain of attraction of the Kingman regime. And now in the last part, I told you when we have alpha between 1.5, then we are in the domain of attraction of the beta coalescent. And if alpha minus 1, so if alpha minus 1 is smaller than beta, so in this regime here, we can show also, so we know the asymptotic fixation probability. But it's not of this Haldane's type. Sn goes not linear into the formula. Yeah, and this was what we wanted to tell you. And now I have some references. Maybe I keep this here so that you know what you have to do.
Oh, Florin.
Still white areas on the blackboard.
Thanks, Cornelia and Anton, for this beautiful tandem talk. I suggest that we unmute ourselves and give Cornelia and Anton an applause. Are there questions or comments or suggestions for the white areas?
Sorry, you have condition on alpha and beta, something like alpha minus 1 is larger than beta.
Yeah, this is this region
but
here.
It is not alpha minus, oh yes, it is not valid. If alpha minus 1 is less than beta, what is the situation?
B is larger.
The opposite situation,
B is smaller.
Larger than, yes.
B is smaller than alpha minus 1.
But if
so
B
if alpha is 1, B has to be 0, so to say, yeah. And if alpha is equal to 2, B can be until 1.
Well, but if B is larger than alpha minus 1, right, then what happened?
Was ist dort los? Warum ist das so?
Right.
Ja.
This is
opposite.
So this is
what will be?
So this is we need this asymptotic behavior to use. So we need this line counting population, really many lines.
Yes, it is negative. If the power is negative here, what will be? What does it mean?
Yeah, then we have only a very few lines, yeah? So we are concentrated around 1. And then we can control.
Anton and Cornelia, I think one of you has to be muted because they're back.
And what is B anyhow? What is the sense of?
Oh, yeah.
Cornelia, can I venture a conjecture? And does my microphone work?
Yes, the microphone works.
Yeah.
I would think that if you're in that world with the domain of attraction of that beta coalescent, and you make the B larger than alpha minus 1, then the fixation probability will just be asymptotically the one of the neutral. So it will be just
it will be 1 over n plus some error terms, and these error terms we don't know.
Uh-huh.
Yeah. Yeah.
That's the thing.
Yeah. You
The
are
leading
right.
order should be 1 on n, I guess.
Yeah, you are right. Yeah.
Because what happens
What is
exactly
B? What
on
is
that
B?
line
Wow.
is another question. What if b equals alpha minus 1?
Oh, sorry, I don't understand. Ach so. Willst du
Okay.
das Ding ersetzen?
Are there
But can you
further
remind
questions
what
or-
is B? What is B? What is the sense of B?
B is the selection, so it gives a selection strength. So we have this moderate
B?
selection.
B?
Which is
Okay.
n to the power of minus
Understand.
b.
Asymptotic of variance. Okay, thank you.
Yeah.
Okay, are there further
Okay,
questions or comments? Or suggestions?
So you had indicated that you had an example which was within the domain of attraction of Kingman's coalescent, and yet Haldane's formula does not hold.
Yeah.
Does that fit somewhere into that picture that you displayed with the alpha and B? Is it possible to indicate where that example lies on that diagram?
Unfortunately not, Jason. This example is more simple-minded. It's more of the, if I am allowed to say, Eldon-Wakely type, or of the beautiful, nice examples which one can find already in Fred Hoppe's nice paper on the slightly supercritical fixation probabilities. I can just tell you the example, right? The example is that you have a paint box where one of the capital N individuals is assigned a weight n to the minus delta, right? A small delta and an inverse power of the n to the, well, say 1 over n to the 10 or whatever, right? And not 1 over n to the 10, but 1 over n to the 0.1, right? A small delta. And so that's the lucky guy that gets a lot of weight, but it's a random story, right? And if you look what here the Holden prediction would be, then we have to look at this n squared times the expectation of the square of this W1. And if you look, then this is a smaller, then this is something which becomes so large, right? It does not, it's growing, right? And therefore, this makes the prediction of the Holden story just impossible, because we then, if we have a small selective advantage, then the ratio of Sn divided by this offspring variance, or asymptotically, it's the offspring variance, would be smaller than 1 over n, which would be less than in the neutral case, right? And some selectively advantageous guy cannot have a smaller fixation probability than a neutral one, right? So it's like in that case that these, if you like, unusual things that one guy gets not overwhelmingly, but a big chunk of the cake, right? That makes the Holden thing obsolete, because the variance would be just too big for the prediction, for a reasonable prediction of the fixation probability, right? But we would love to, of course, have still more substantial counterexamples. For instance, in this region, right, around 2, right? And there is still one comment to make. There can be 2 reasons for a failure of the Holden formula. One reason could be that the branching formula already is corrupt, like these examples in the Hoppe paper, right, which have a similar spirit than the one I just told you. And the other reason could be that the branching approximation fails in the early phase of the Canning's model. But that seems to be very robust, right? We don't have really a stringent example where the branching process approximation dramatically fails, right? It's just on the branching side that these things, we can always say, of course, there are too many collisions and we cannot apply the techniques and so on. But this feeling of the big guys like Fisher and Holden and so on, that in the early phase, the branching approximation is just good, right? Even when you cannot control all the collision-free stories and so on, that seems to be very robust. So we would love to have more insight into these tabulae rase, into these white areas on the map, which you still see.
Okay, thank you.
Yeah.
Are there further questions or comments?
Yeah, I think Matthias Birkner and Julia and co-authors, they have a result that at least for also these branching processes, the fixation probability are also asymptotically equal to the same formula that we get here.
Right,
so,
but maybe just since we have Jason in the audience, which I like a lot. Thanks, Jason, for being with us. We didn't touch another important class of Canning's models. These are the ones of, I should say, Schweinsberg type, right? Jason came up in 2003 with this proposal that one should take a supercritical branching process and every individual just makes a supercritical offspring. And then you sample from this offspring. And you just need to condition on that the offspring is bigger than n, which is an easy task for a large n because of the law of large numbers, right? And these Schweinsberg Canning's models became interesting and in the modeling of experimental evolution some years ago, right? This was a project where I was involved, and also Adrian and Noemi and Ling Long. And this was actually a predecessor of this, what we had here, but it's sampling without replacement. And this brings then us to the root, which Cornelia, thank you that you, namely Matthias Birkner and Bjarke Elden and Julia Dahmer, they are working, and of course Matthias can tell much more on this, for some time already on these Schweinsberg type models with selection, where there is another kind of selection going on, that the sampling is biased towards the fitter types, not that they get more offspring, but the sampling is biased. Highly interesting things. And it seems that this generalized Holden formula in the regime alpha between 1 and 2 is also very robust. Namely, Matthias, we had this nice phone call yesterday in the late evening, and you explained me that you have a very similar formula to what we see here in this corollary on the slide, but you can explain it better. How was your vaccination today, Matthias?
Okay, I don't know, you're telling everybody, you know, we're being streamed on YouTube.
Yeah, but
I can stop the slide streaming
know
at this
that,
point if you're going to
okay.